Good afternoon. My name is Asif. I'm a technical business development manager for containers at Amazon Web Services. So in the next 45, 50 minutes, we're going to talk about why would you use containers and how containers enable you to drive innovation faster through your development pipelines. How many of us are using containers in production today? Oh, that's nice. I better be careful. Okay, warm up. Cool. So, and I've got with me Chris from WeWork, and Josh from WeWork, and Radek from OpsLine. We're going to talk about how WeWork, which is one of the premier startups in the co-working space area, how they use containers to drive agility and innovation through their development lifecycle. So let's get started. This is how we used to build software. I'm a Java developer by birth, or by my software birth. But the idea was I've coded through different parts of Java application, and we used to build these monolithic apps where apps were all intertwined. And if you wanted to change a UI, let's say I'm testing a new feature which I want to be geolocated for this audience here, it was really hard. I remember a time in my life where a UI change caused so much ripple down the tool chain or down the development workflow that we had to spend 2 full weeks just unraveling that. And that was not agility. That was the opposite of agility. So we used to build, test, release, delivery pipelines, and get there. A lot of challenges in that space, and none of this is new to all of us. All of us have coded these. So it's very difficult to scale those applications. You have to go vertically scaling. And vertically scaling, yes, it works, but only works to a certain degree. Then I talked about long build, test, release cycles where every change, every minute change has to go through that regression and things like that, and the whole intertwined thing. I used to like colloquially call this the spaghetti architecture, because if you've looked at a monolithic code down there, and how this is calling different functions, and if you really want to draw it out, I'm hoping you could draw back, something more cleaner, but I always ended up drawing a spaghetti where lines are going from here to there, and you're like, okay, I don't understand this, but these are the challenges. And at the end of the day, what happened was customers would come back and say, hey Asif, why does it take me 6 months or 12 months to see a feature from you? This is not acceptable. I need those features way earlier. Now, rewind that back. 2005, 6, and I'll talk about that later, is when monolithic apps started getting broken down into microservices. And microservices at the core of it, and microservices is a more fancy term for service-oriented architecture with easier protocols, and we've all done service-oriented architecture for a long time. So microservices enabled us to do this isolation and do one thing and one thing really well. I have lived a life where people used to tell me, you can only do a Java stack app. The whole stack has to be Java. So we wrote a UI which was struts, backend which was pojos, and yes, those frameworks are great, but as a developer, I did not have freedom. I crave freedom. I should be able to choose the tools I need, the language I need. With microservices, you can go polyglot. Your UI can be running JavaScript, your backend could be running Python or Java or something else, and so on and so forth. So let's dive a little deeper and talk about what really is microservices. I'll quote Adrian here, Adrian Cockcroft. At the time, he was with Netflix when he said this, I believe. But microservices is a service-oriented architecture. What it means is services talk to each other over the network, and they are fault-tolerant and highly available and disposable and resilient. So I have the same code base deployed in US East 1, and I have the same code base deployed in AP East 1, and it exactly works the same, and all the dependencies are taken out, and I make it disposable. The second big feature of microservices is the service-oriented architecture is composed of loosely coupled elements, and I cannot stress more about this. One of the biggest software pain points or sacrileges that happens is when we get into tight coupling. How many of us has seen dot properties file with hard-coded variables? Okay, you guys are amazing programmers. This side is amazing. This side is like me. So, but the deal is this. So when you tie your software or your APIs together through very opinionated constructs, you will, every time you want to change it, you'll have to go through a bunch of things to make this work, and that causes lack of agility. And finally, you have to live in bounded context in a microservice. And what does this mean? A bounded context means, in very simple way of thinking, is it does one thing and one thing really well. So take a step back. If I'm writing a UI, an order management UI, I should not be worried about how a payments UI looks like or how a social feed UI looks like. Those are different visualizations, and those are different ways to interpret the same function. If you focus on giving the best order management experience to your customer, and you have decoupled it, you have created a microservices architecture that can go faster. And who did this? We, at Amazon, did this way back, I believe, in 2005. So when you look at Amazon.com today, when you go to the website, it's comprised of a bunch of microservices. Each of those boxes that you see is a microservice or is a group of a set of microservices that is powering it. So the customer feedback that you say, the customer reviews, the add to cart, and each of these has been built to do one thing and one thing really well in a very loosely coupled way, and it's powered by the service-oriented architecture that we are used to. So if I've done all of this, what does this get me to? It gets me to getting my code more agile, more flexibility. I can move code from between regions. I can upgrade faster. My developers can write code at their own velocity. So your UI can run at their speed, your backend can run at their speed, and your data access layer can run at that speed for a 3-tier architecture. And each of these layers have API-based contracts. It's like in English language, we have a contract of communication. So when I say things like, hello, how are you? The contract is that API is understood, and the answer comes back, say, hey, I'm fine, how are you? So those are API contracts that need to be defined, and if you have defined those, the agility comes faster. Imagine having the same conversation if we didn't have syntactical contracts in English language, where if I say, hello, how are you? What comes back is a random text string or something which is different. Then it will be much harder to communicate with each other. At the end of the day, when Amazon did this, this is what it meant for Amazon. Thousands of teams building microservices through continuous delivery, and it ended up as 50 million deployments a year. This is a little dated metric, but anybody wants to take a guess how many deployments are happening a day or a second if somebody really wants to go for it? No? Okay, a lot, that's correct. That's one deployment every half a second, like sixth of a second. That's the speed microservices and containers provide you. 5,700 deployments. This is unimaginable in my life. Like I'm pretty sure you guys have better engineering workflows, but where I come from, in 2008, this was unimaginable because a set of 50 deployments used to take us weeks, not even days. But when Docker came in, and this is like we used to package using Maven, and Maven had its own good and bad, but Docker came in, and Docker gave us that CLI, that easy way to package the application runtime, the OS, the dependencies of the applications. I can even put in environment variables now. I can do port binding. All of that has become super simple to build, ship, and package it and run it. Doing one Docker container is super easy. I can go to my laptop and fire up a CLI, and boom, it works. But doing this is super, super hard. This is, think of n nodes with m containers each, and you've got an O of mn problem, O of n square problem. which is a hard cluster management problem. And that's where you need a container management solution that does this for you, like kind of does the undifferentiated heavy lifting. So container management platforms, a bunch of them came through approximately the same time. Docker came out with their own one. There's Kubernetes out there. Amazon, we looked at our primitives and we launched Amazon ECS in 2014. And there are others also that are pretty popular. But at the core of this whole container management story is running these containers super, super easy so that you or we as developers can focus on writing the code. Once I've packaged my binary, everything should happen. Like there's a saying that I use is, developers don't care only when the platform is stable and does not break. And I truly believe this as a developer. Imagine going to a platform, a container management platform or any platform which breaks in production. The common example is, and noding to Jenkins is, Jenkins plugins used to fail in production. And then the whole engineering team goes back and starts troubleshooting that plugin. That was wasted cycles, bad customer experience. So going back to developers don't really care about the infrastructure or the container management platform when things work. And that's where what we focused on ECS, and we built a platform that many customers are building, scalable and production workloads on. So at the core of ECS is a cluster management service. So there's a key value store, which is a Paxos-based database journal. It's basically a state transition machine that we keep. Once you have a cluster management service, you can store the state of your nodes and the state of your containers in that journal. All this is powered by API, and we have an agent communication service. Naturally, if I'm a container and I'm sitting on an instance, I need to talk to somebody, a cluster service, to do it. That is ECS. ECS is that orchestration and the management engine that does all of this for you. On each instance, containers runs on EC2 instances. On each instance, we have an ECS agent, and that agent communicates back to the agent communication service and keeps track of the whole cluster that you launch. Imagine launching a cluster and trying to keep this in balance. Today, you can go on the ECS console or the API and say click cluster, and it works. You can have a 500 node cluster in no time. And that's what ECS provides, apart from the deep security integration, AWS, other services integration that we'll talk about. On each instance, when the containers are sitting, they're grouped together into a logical unit called tasks. You might hear pod also in the Kubernetes world, but we call it a task from a nomenclature. And you can have up till 10 containers in a task, but think of it as kind of a business function that you can wrap together. I have customers who have ripped out the UI and called it a task. All the UI's components are running in one task. I have also customers who have basically done a vertical slice and says my UI, my backend and logic, and my data access layer sit in a task. And you can scale these tasks horizontally. You say, I want to run 10 tasks, it does it with autoscaling without you going back to see if it works or if the lights are on. It just does it. So scaling comes naturally off the bat. You can front it with a load balancer, or what we call also a logical construct called service. When your internet traffic spikes from 10 requests a minute to 1 million requests a minute, you need a shock absorber. And that shock absorber is the load balancer. There are two load balancers on AWS today. There's application load balancer, which is a layer 7 load balancer, and a layer 4 load balancer, which is the network load balancer. And it does different things, but both of them integrate deeply with ECS. So if you have a TCP-based workload that you want to run on containers, you can go with NLB. If you have an HTTP-based workload, you can go with ALB. So at the very high level, that's what ECS is about. But it's not just about a container orchestration platform. And I want to take a pause and say this again for myself. It's about the whole platform, what BuzzFeed told us. And when you look at developing a microservice, or on a container. Deployment on a container management platform is one piece of it. But then you have secrets management, service discovery, load balancer, task networking, auto-scaling. All of these are super important when you're running microservices at scale in production so that you can go sleep well at night, and at 2 in the morning, when a pager buzzes, it buzzes on Amazon. And that's where, when we are developing microservices, look at the platform, how the AWS platform is innovating in the cloud-native way, and use that cloud-native constructs that AWS is providing you to power these things. And of course, you can use open source on top of AWS. So with that, I'd like to take a pause and invite Chris to talk about what WeWork did with this.
Thank you. Innovative with containers on AWS ECS. So I'm from WeWork. My name is Chris. I'm a VP of Software Engineering. And I don't think it's always so straightforward in order to just be innovative and make things happen in production. A lot of people are risk averse, and they should be, because there's time and money on the line. So a lot of startups are very chaotic. And our startup was pretty chaotic. We had 3 different ways to deploy: Elastic Beanstalk, Chef, custom shell scripts. We had security that was basically done by people super fast, super light, way too open, and we had a lot of variation in our infrastructure. So after 810 days of uptime on this EC2 instance, it started to fail. The network card just stopped working. It made me pretty sad. Pretty much dodged a bullet on this one because I had basically nothing to do, just sat there and said, okay, well, it stopped working, and now it started working. Is it going to happen again? We really weren't prepared to set up for our stack on a new set of hosts. So I knew it was time for a big change. We needed to quickly be able to recreate our environments, get it ready for much more scale as WeWork had acquired our small startup. I needed to secure the platform, as well as begin to adopt the DevOps culture and keep things simple, which I later learned to be using a cloud-native approach. Let me turn this over to Josh. He's going to get into more of the details and introduce you to Fieldlens.
Thanks, Chris. I'm Josh Davis, principal engineer at WeWork. And let's see. Yeah. Before I go into the details of how we're using ECS and all that, talk a little bit about the application Fieldlens. So Fieldlens is a construction communication app. It's designed to help construction teams communicate about the status of the project and to track their progress and generate reports for stakeholders like owners and architects and engineers. How many of you use Jira or Trello or, yeah, pretty much everybody. So for you guys, Fieldlens is Jira for construction. That's it. So while we don't have the scale of some large social networks like Facebook or whatever, you can see from these numbers here, we have millions of pieces of content, about 80K users, 110,000 projects. That's a good amount of stuff, and we need to think about scalability, especially since we were acquired by WeWork, and WeWork does a lot of construction. We have different clients. We have the app is very mobile-centric, so we have construction workers on job sites, walking around with their iPhones and Android devices, taking pictures of stuff. Oh, this toilet was installed in the wrong place. That kind of thing. And those mobile clients have a different workload than the web clients. We also have background jobs. We have to generate reports. We have to process blueprints, which come as PDFs. And so we have these sort of long-running, compute-intensive things. And that is really difficult to do if you have a monolith and you're running on manually created infrastructure. It's really not the way you want to go. And enterprise users expect reliability, and our users have hammers. So how we started, we didn't start from nothing. We had already had, before we decided to go to ECS, we were already using Docker Compose to set up developer workstations, to set up things like database servers, Elasticsearch, ElasticMQ, things like that, so we could develop and we didn't have to deal with people setting up their database incorrectly, things like that. We also had split up some of the monoliths. We had some microservices, usually based on the workload that they were placing. Those particular activities were not really compatible with an API server, which needs to serve lots of little quick requests. You have a report running for half an hour, and that's no good. So we'd split some stuff out already. And we already had a full Jenkins build, test, CI/CD pipeline. And we have a bunch of environments. Now here's where the consistent deployment comes into play. Our environments, one of them was using Chef to deploy things, another one was using the custom shell scripts and tarballs and stuff like that. It really got to be a pain when you're working on something and you've got the development pipeline working fine, and then, you go to QA and, yeah, right, the deployment script doesn't do that. Really, we need to step it up. So, where do we want to be? We agree on Docker images for everything. So every service, every microservice, every monolith, everything is deployed as a Docker image. That's our deployment unit of choice. Everything is contained in the Docker image. Also, uniform deployment and management, right? So if an engineer or an ops person wants to take care of the web app versus, or this part of, some blueprint handling service, everything's deployed the same way, everything's managed the same way, and it just makes life a lot easier. Also, since we have monoliths, I'm sure some of you probably have monoliths, you want to make new microservices easy to create for the developers, right? You want to give them as much control as possible. And you want to encourage microservices, right? And last but certainly not least, we want enhanced security, scalability, reliability. ECS pretty much does all those things right out of the box. So this is our desired typology. We have a secure network, VPCs, for every environment. All the resources are deployed in that VPC. We have a front-end API router for cross-cutting concerns like metrics, logging, and security monitoring. And we have the ECS scheduler deploying all the services into the ECS cluster. Another thing to note is it really helps, especially we had some services deploying Elastic Beanstalk, really helps us use our EC2 resources more efficiently, because we can deploy a lot of small resources on maybe larger servers. Again, it's just freedom. We can tune everything and come up with the best solution. So here are our services running in our different environments. So this is sort of the end state. Everything's managed from, this is a snapshot of the ECS console. And it took us about 8 weeks to get this done. That's not a lot of time, is it? But as I mentioned, we didn't start from nothing. So how do we get there? How do we get to start using Docker in production and stop just using it as a sort of developer workstation play area? First step is to start building and publishing Docker images, right? Because we agreed that that's going to be our deployment unit. And we're going to build Jenkins pipelines. We're going to learn how to publish images to an image repository. We selected JFrog Artifactory because our Java applications, we were already using it to publish our own libraries to Artifactory. and various pieces of commercial libraries that we were using. So that was sort of a no-brainer for us. And the main goal here is to get to a point where we have a Docker Compose-based infrastructure running on the developer workstations that will deploy all the services on the workstation, on developer's workstation, and then they can kind of just not start the one that they're going to be developing on today, right? And then start the development environment for that specific service that they're going to do work on. So here's what that looks like. We created a local infrastructure Git repo, which basically just has a Docker Compose file in it, which pulls down all of the dependent services that we need on the workstation. So here's, and it also would have some, we also have some shell scripts there to help developers start up the things that they need, all your dependencies. And that includes the latest versions of other services that are written by other teams or what have you. Then when the developer is working on a specific service, inside that service Git repo, there's another Docker Compose file which connects up with the Docker network created by the infrastructure one. And so the service under development can connect up to all the other dependencies. And then we volume in all the build output on that developer's workstation so they can do a build like they normally do right on the host and then map all the files in and restart the application and open up debug ports and attach profilers and all that stuff. Okay, so that gets us to our first milestone. We have all our services working inside the container, right? So during this process, all the developers are trying to get each of the services to be containerized, self-contained. And yeah, so we have the whole thing running there. We've established a basic configuration for every service. And we have Docker files and Jenkins files for all repositories. And we're all pretty familiar with how they work and all that. And yeah, so the dependencies, as I said, are connected via the Docker network. So you can work on a service, and you can have all the other services there. So we're ready to go to the cloud. And I was thinking I should call this slide Meanwhile in DevOps land. While we were doing all that on the development team, the ops guys were busy making CloudFormation templates. So we decided to use CloudFormation as our infrastructure as code weapon of choice. And we had two sets of templates. One is the environment templates. Those set up all the basic features, and it's a little bit like that Docker Compose infra repo I talked about. It sets up all the basic resources, ECS clusters, RDS databases, VPCs, all kinds of things like that. And then you have service-specific templates, which we put in each repo. So again, that gives the developer access. When you check out service XYZ, you have everything. You have your local Docker Compose file, and you also have your ECS CloudFormation templates in there, and all the parameters files for each environment. I'll go into that in a second. And then we have another repo containing common shell scripts to make it so we don't repeat ourselves so much. So, environment templates. This is pretty easy to understand, sort of high-level view. So it's just a repo with a bunch of CloudFormation templates for each environment. Also, this makes it really easy to make new environments. You just copy the template, make some changes, boom, you got a new environment, run it. In case one of the environments needs to be recreated for any reason, this is one of the goals we had, there it is, CloudFormation, just run it, boom, you got your environment back. So service templates, this means we go into each service and add CloudFormation template there for that service, maybe more than one template. And for each environment, we have a set of environment parameters that we use with CloudFormation to fill in the parameters specific to that environment, like where's the database and things like that. And so this is where the developers and this is where DevOps happens. Developers and Ops team get together. Ops team creates the general service template based on what the developer is talking about. We try it out, we iterate, deploy it over and over again, and get it to work. So one thing that was a common theme among some of the microservices is many of them use databases, relational databases. I like relational databases. Sorry. Yeah. So we had to figure out a way to update the database schema, but we didn't have the sort of synchronous, sequential, self-script deployer that we used to have, right? This is CloudFormation. You're telling it, OK, there's a new version of the code over here, go do stuff, and we'll wait until you're done. And it does, it does everything eventually. And you really don't have a point where you can kind of get in there and know, like the system is in flux until it's done. So we decided we would try this out, and it worked great. We would make a task just for doing the schema update. And we would create a new version of the task definition and run the task like a single run ephemeral task on the cluster, update the database schema while the old version of the app was running, and then do the deploy. This actually worked really well. The main caveat here is that your schema changes have to be backward compatible with the previous version of the app, or you'll break things. And then, remember guys with hammers, So the other thing is secrets. So, like many of you probably do, these services we have, they have API keys to various other things. We don't want to. We want all the configuration and version control, but we don't want it in clear text, definitely. And we don't want everybody to know. We don't want all the developers to know all of our API keys for everything, right? So we came upon the solution of using Amazon KMS. So what we do is we encrypt the sensitive configuration components with KMS, and we store the encrypted files in Git. And so the developers are able to decrypt, make changes, and check and commit it and push it. And the privileges are controlled by IAM privileges, which is great. So you can, for example, restrict certain developers cannot access the production secrets. And furthermore, the Docker images contain the encrypted configs. So it's fully self-contained. Our Docker images have everything they need. And the last little bit is while the containers are starting up, everything gets decrypted. Another challenge we had is we use a technology called Hazelcast, which clusters the instances of this application together. It does things like caching and distributed queues, distributed locks. It's actually really cool. Unfortunately, we don't have multicast IP or any other way of really for the nodes to discover each other and federate into a cluster. So we came upon the solution of using console to register all the nodes of the cluster there. And we use something called Container Pilot. And so that, again, it's part of the startup of the container. The container starts up, registers its outside address of the ECS instance with console, And then as it continues, it does a query and says, OK, what other nodes of my type are out there? OK, I'll start federating with them. So here it is in action. This is sort of our develop branch. We happen to use the Git flow way of doing things. I don't know if you're familiar with that, but our develop branch is a full CI/CD pipeline. And so the Jenkins pipeline does the build, deploys the new version to JFrog, then invokes the deployment scripts, and that goes through CloudFormation. The environment parameters and the CloudFormation template then deploy the containers to ECS, and that pulls down the newly built image from Artifactory. Good stuff. So some other details that we discovered along the way, which might be kind of interesting. I mentioned this thing, Container Pilot. That's sort of a generic entry point tool. I don't know if anyone's looked at that, but that really helps quite a bit in terms of managing the process, or maybe if you run more than one process inside your container. It can really help simplify that, and it tremendously simplifies working with console. The other thing is logging startup while the container is starting up, your entry point code, basically. You need to log that. You need to know where those logs are, because when you make mistakes and you mess it up, you need to be able to go find out where that is. And also application logging. We happen to use log entries, so that was a thing we had to deal with there. Additionally, we had some services that are singletons, where we couldn't have more than one of them running at a time. For example, we had a service that receives incoming emails. You guys use Jira, so you can get a notification from Jira, and you can say, OK, I got it. And it ingests the email and makes it a comment. So we have a similar feature. That thing, you can't have more than one of them. So figuring out how to do singleton services actually is quite easy. You just set up the number of instances that you want of the task. And then this idea of promoting builds to environments. So one of the big things that I always strive for is the artifact that you run your integration tests on, all your unit tests, all your integration tests, and all your manual QA, whatever you have, that's the thing you want to go to production with. You want to put that in QA. QA gives you the green light. You want to take that binary thing and then put it in production. Because nobody ever has merge conflicts when merging to master, right? Yeah. So anyway, we ended up building a second set of Jenkins jobs for each service where you could select an image and then go to QA or go to production. So we could do our master build, deploy it to QA first, get the green light, and then go to production. So obviously, it's not all, there are things that we had to deal with along the way. Mainly, in making our services self-contained, we ended up discovering a lot of configuration that we kind of didn't know we had. So that's a good thing, though. It's a good result. Like I said, log entries. Getting the container startup and the container standard out and standard error to go to log entries. We ended up doing a sidecar. Is that? Yeah, sidecar for that. As well as Datadog. We make good use of Datadog. Had to make more sidecars for that. Had to figure that out. In addition to application performance monitoring, we use TraceView. That needed an agent as well. So a bunch of agents we needed to start. Also, when it was in production, we discovered that one of our monoliths likes to open a lot of files, likes to use a lot of file handles, so we had to raise the ulimits because it kept falling over. But again, really simple with ECS. It's right there in the service CloudFormation template in the Git repo for that service. It's great. So that was quite an easy fix. And so the main thing, though, is that deployment is really different. You're no longer running a shell script that's going over and copying things around and starting servers and shutting things down and all that. You're setting some stuff up in CloudFormation, increasing, bumping the rev count, and then saying, OK, go. And then it kind of figures it out by itself. So it might take a little longer. You don't know where it's going to deploy to first, so kind of going over and SSHing over to a server and looking at the logs on that server as it's coming up. Forget that. It's not happening. You got to set up your logs correctly. And you got to make sure everybody knows where they are so you can see if there's any kind of problems. The other thing is, if you have some misconfigurations, the ECS scheduler may shut down something that it thinks is unhealthy and then bring it up somewhere else and then shut it down again and then bring it up somewhere else, and it'll start to cycle and flap. You got to have the troubleshooting tools there. So that's it in a nutshell. With even more detail, I'll hand it over to Radek from OpsLine.
Thank you, Josh.
Yep.
All right. Cool. My name is Radek Wierzbicki, and I'm a solution architect at OpsLine. We provide DevOps building blocks for agile engineering teams, including infrastructure management and DevOps culture enablement, which is, I think, more important. We have helped to implement DevOps strategies for many products and services that you are using every day, including WeWork. We have been working with WeWork on Fieldlens project, providing configuration management and automation for several of their applications. When we started working with WeWork on ECS, there were 3 approaches to application deployment. They were all created by different teams. Each used different techniques for local development, infrastructure management, and pushing releases to production. Although a lot of automation was in place, there was a lack of unified approach. At OpsLine, we believe in cloud-native approach. We are using CloudFormation to automate almost every aspect of deployment into AWS. We have built a set of reusable CloudFormation templates to help us provision infrastructure environments very quickly in multiple accounts and regions. We have automated provisioning of virtual networking, network security, access control, and all the services such as EC2, ECS, ODS, and Lambda. We also version control not only CloudFormation code, but the stack information. Changes are deployed using a simple script and continuous integration tasks. Since we are talking about containers, let's talk about the reasons we picked ECS to be our container runtime environment. ECS solves one problem that we are always dealing with. It's scalable and quick application deployment. A task of taking the code from hands of developers and deploying it in a highly available and scalable manner. In the past, we had to use configuration management tools like Chef, as well as orchestration frameworks like Capistrano, Gradle, or some custom scripts. And ECS simplifies all that, just like ODS simplifies database provisioning and management. ECS clusters are easy to provision, and ECS services nicely encapsulate and manage Dockerized applications. Amazon EC2 Container Service makes the most sense to use AWS because a cloud-native solution is easier to manage without acquiring all the underlying knowledge of other orchestration frameworks. With our in-house expertise and experience, we have provided what we think is a practical approach to deploying applications in ECS. So let's talk about underlying EC2 Cluster Management that supports ECS. We have created a CloudFormation template that can launch a fleet of servers. We are using autoscaling groups to provision clusters of AWS Linux instances running ECS agents. We are able to create clusters with different types of instances that accept different profiles of applications. We can provision a memory-optimized fleet to run memory-heavy applications and a compute-optimized fleet to run applications that can crunch numbers all the time. For configuration management, we're also using native AWS tools. CloudFormation init framework nicely fits in our use case, providing a way to configure ECS agents, as well as download and execute custom scripts. All that within a single CloudFormation template. Monitoring is also an important part of maintaining a cluster. We are deploying Datadog agent to every EC2 instance using CloudFormation init. We have designed a solution to launch and manage an ECS task on every instance of an entire fleet. Now I'd like to spend a few moments on autoscaling. Autoscaling enables us to react to changes in demand for cluster resources. We scale the EC2 instances out when we notice that resources are getting thin. Let's look at an example here. Let's start with a ECS cluster with just one server. It has 4 CPUs and 4 gigabytes of memory. We are running 3 tasks on it, each taking different amount of resources. The server is reserved in 100% at the moment because all 4 CPUs are reserved. Adding more tasks to this configuration will leave them in a pending state until we add more resources. And once we do that, they will take space on the second server. At this point, our CPU reservation is 88%, and we could start maybe one more task, but not many more. ECS provides resource utilization metric that will let us drive EC2 autoscaling. In our example, we can configure it to scale out when the CPU utilization is greater than 80% and scale in when it's less than 45%. One important thing to note is that resource utilization metric only counts running tasks, while all the pending tasks will not be included. So now let's add a few more tasks to the cluster. At the autoscaling configuration I just mentioned, it should have already provided an additional server for us. Another important fact to remember about resource utilization metric is that it's relative and it's expressed in percentages. The value of the metric changes depending on the number of servers in the cluster, even when the amount of free resources remains the same. The CPU utilization with 2 servers was 88%, and it's 92% with 3 servers. So what I'm trying to show you is that it can be tricky to get all the values correctly. Now that I have shared how we provide resources to run applications, let's look at how we prepare our applications to run on the ECS cluster. Again, we are staying cloud native and using CloudFormation to manage the entire application lifecycle. Each application has a template included in the source code. It's parameterized so that we can deploy an application to different environments. The template creates ECS service resource, the ECS task definition, 1 or more container definitions, an IAM task role, and if required, an application, elastic, or network load balancer. The IAM task role provides access control to AWS resources for the applications. Running containers have access to limited set of resources, such as S3 buckets, SQS queues, and KMS keys. We restrict that access per environment so that, for example, containers running in a development environment can only access development S3 buckets, and at the same time are forbidden from accessing the production buckets. And in most cases, this is achieved by naming conventions over configurations. We are utilizing different techniques to monitor the health of our containers. For web applications, we are using a coupling between the ECS service and the load balancer. Additionally, for the applications that take very long time to bootstrap, we have developed a simple container that we are running alongside an application. It covers an edge case where the load balancer's health check is set to a very long timeout and will not trigger fast enough when the application is already up and running. In addition to health checks, we deploy Datadog agents to every EC2 host, and all running applications can then submit metrics to a local statsd process. We also enable Datadog's Docker integration that provides a multitude of system-level metrics for us. As we have seen before, we are using CloudFormation to manage the entire lifecycle of an application, including the deployment. To deploy a new release, we have to update the CloudFormation stack with a new parameter value that signifies the Docker image version. This action requires a replacement of ECS task, and the ECS service performs a deployment based on the parameters that we specify for each application. So let's look at another example here. Here's a 3-node cluster with 2 running tasks. Once the deployment is triggered, the ECS service starts a rolling task replacement. It will add 1 or more of new tasks, the new versions, and the number of tasks to add depends on the batch size. Once the new tasks becomes healthy, the old one will be removed. And at the end, we are left with the same number of tasks, all running the newest version. Our production deployments ensure 100% capacity to be available. And additionally, we can update any stack parameters on any deployment as they are versioned with the application code. We are able to change the capacity, update the load balancer settings, or CPU and memory requirements. The EC2 Container Service achieves what every system administrator always wanted: the ability to run applications on a ephemeral cluster of resources. But try explaining this to developers and tell them they can't log on to servers anymore. Everyone needs to understand that container instances are ephemeral. It's not important where they run, but it's crucial that every engineer has access to log files and performance metrics. We need to have proper monitoring in place that notifies when issues occur. And when errors do happen, bad containers should be removed and then replaced with the new ones. Another important thing is to empower developers to easily integrate their applications with ECS. We need to provide them with guidelines on creating efficient and secure Docker images. We also provide them a code repository with a generic CloudFormation template, deployment scripts, and CI/CD integration examples. To sum it up, I hope we were all able to show you that using cloud-native tooling can deliver a consistent and efficient application deployment in ECS. With that, I'd like to turn it over back to Chris.
Thanks, Radek. Thanks, Josh. As you can see, it took a partnership between engineering management, platform engineering, and DevOps to put our minds together to think about a DevOps process and culture that works for everybody. So WeWork was successful because we brought all these people together. I firmly believe that managing technology change means seeing the bigger picture, but taking small, incremental steps to solve problems that are clearly defined, that have a problem statement and a solution statement. This actually turned out to be a cloud-native approach, and I'm super proud of the work that the team did. We're hiring at WeWork. If anybody's interested, please send me an email, see how that WeWork. And with that, let's open it up for some questions.